Welcome back. Today I want to talk about a problem of creating data sets that provide us with other functions. Some programmers may know this as a function factory. It's a very common technique where we know that the types of functions that we're going to be interested in are only a certain class of functions, and that by knowing they're a certain class, we have shortcuts for writing them very efficiently. Suppose that I'm at home making salads, and I need to provide a nutrition chart to sell them at the Saturday market. When I create the salads from my recipe, I know exactly how many of each ingredient go in, but I would struggle to predict how much protein, calories, and so on are available in the salad I've made. And that's because I lack the chemistry, the lab that would explore how much vitamin C is available in this fruit salad. If I go to a website that contains this type of information, I'm very unlikely to find my specific fruit salad in the list of described ingredients. Instead, they'll feature ingredients like apples, grapes, pears, melons, and other fruits. Those are the things that the lab can predispose itself to testing, and it can test it under many scenarios, such as where it's imported from, what kind of cultivation strategies, organic or non-organic, what kind of watershed. So the values may change based on these particular parameters. In order to produce the eventual nutrition chart, I'll need to combine what the scientists have explored on individual ingredients with my salad. We could change the recipe and use the same nutrition chart and provide the nutritions for all other types of recipes, provided all ingredients appear somewhere in this data. Each nutrition chart generates one function from recipe to nutrition. And likewise, we could reverse it. Each recipe could produce nutrition to nutrition chart. So we've just seen that not all functions are created initially as functions. They might be stored as other types of data, such as a nutrient chart. In the situation we have, we're exploring that the USDA has provided us with fixed nutrient charts, which will be updated periodically, but they're stored in a compact way, which would save us the need to reprogram it every single time. Instead, we'd like to be able to generate a new function whenever there is an update, but otherwise think of it as unchanging. Meanwhile, the salad recipes will change from one consumer to the next. We expect that to be input data from our user. The goal is to combine these two charts to provide the nutrition label. We simply rescale the quantity of each ingredient that occurs in our recipe, thus providing the amount of total proteins, fats, carbs, etc. for each individual ingredient. We then add up all the ingredients to get the total in our salad. The right combinations come from our various recipes. Recall that when we create a new data type, we start from two logical connectives, introductions and eliminations. Introductions become a formation rule and then an introduction, a constructor. Elimination rules become our getters, and the computation rule puts it all together logically. In time, these are translated into programs in specific programming languages, such as Java, C++, Haskell, and any number of programs. If you need more detail, we made an entire playlist on this, which you can watch or rewatch. We start out with two data types, A and B. In our story problem, this was recipes and nutrition labels. What we wanted to do was create a new type of data, the exponential. The exponential we denoted by B to the A. This was our formation. Once we've formed the new data type, we want to have introduction and elimination rules. Here we have actual choices to make. We have two ways that we could do this. One is we can lean on Cartesian pairs. We could pair the exponential with A to make a pair of inputs that produce the output. This was the same as taking a nutrition chart together with the recipe to form the nutrition label. But there's a second way we could think of this problem. Often what we want to do is use the particular chart many times over. So we load up the initial chart and we create a function that will read anyone's recipe and produce the appropriate label all at once. Either way we think about it, the data is the same amount of data. Either we take individual pairs and evaluate them one at a time, or we pre-compute the function we need and apply that function many times. This may have advantages depending on the engineering that you have in mind. Creating this function might make it faster to apply multiple times, but it may use a lot of memory. Whereas this one might be slower between particular runs, but it doesn't require a lot of resources. Whichever way we think of it, we have now created this function factory, the exponential. Now, this is so far only an elimination rule. Notice these two elimination rules, while interchangeable, are not the same as a cone or a cocone. That is, we are not simply taking all the arrows from our data type into these data types or the other way around. It's a brand new form of universality. This is just a demonstration that the concepts of universal programs can spread quite beyond the ones we've seen simply with the examples of cones and cocones. If you'd like a review, you can watch our videos on cones and cocones. Our objective right now is simply to make our program robust for the future changes. If someone should come up with a future design that's better than ours, we would like to import their ideas or export ours into their format. Either one would make our program resilient for the future. In that sense, it would be a universal program, one that anticipates it will need to adapt to the future. So, what do we need to compete with an alternative solution? What we do is we match the same syntax. We assume that an alternative comes along that replaces our exponential with better or alternative engineering. That means the shape of the functions should stay the same. Since we have our choice between elimination styles, either producing a pair into a function or a function into functions, we should assume the alternatives could come in either flavor as well. Let's draw the two alternatives. Since we have elimination rules, we should look for some introductions to our data type b to the a. We can get those by comparing with the alternative and asking that that data be mapped into ours. This is exactly what we would want to get started anyway. Remember that the alternatives don't always represent future advances, they also represent the past. For example, this could be the website from which I download the initial chart. That method is very slow, and I want to convert it into my internal storage where I can access it very quickly. That's an alternative that I want to swap out for an even better one. The future discoveries that change to a different file format are also allowed as introductions. So let's add these introduction rules. So what rule are we missing? If you watched our videos on creating data types from logic, you know that we're missing the computation rule. The computation rule is about creating cohesion between what we need to eliminate and what we introduce. If these were independent roles, they would never talk to each other and we would never know what the data is about. Let's take a look at the option 2 version. If we have an alternative, such as taking the data from a website, we might want to internally store it for quick access. But if we just read it off the website, then we can take future recipes and compute the nutrition label directly from reading it off the website. We should be able to produce the exact same nutrition label on the exact same recipe using our at function. What this means is that we leave the a and the b values unchanged. When we leave things unchanged, we like to use the equal sign. We are not changing the functions that come out of these two different types of applications. Now let's take a look at the ordered pair version. With the ordered pair version, we don't make an intermediate function. For example, in this situation, we might evaluate it one at a time. This might be an engineering solution that solves it for low power modes or low memory access. In that situation, we don't change the inputs. And the result will be we also don't change the output. Transferring that to just equations, we see that it's just a matter of two different types of notation. In the first option, we're saying that we create the exponential c to the f. That might be writing our data set in some new format. Then, when we apply it to a, it produces the same result as applying f to the pair ca. If we don't want to deal with pairs, but we prefer to have iterated functions, then c to the f is a function which takes values of type a and returns values of type b. That's from here to there. So, taken together, the formation rule takes a pair of types a and b and creates a new data type b to the a. As an introduction, if we find an alternative approach that takes pairs from C and A into B and has a value C, then we can create a value in our data type C to the F of type B to the A. That'll introduce data to our new method. Correspondingly, we need to be able to evaluate data of our type B to the A on any input A. We write that as F at A. Finally, the computation rule is that any alternative should match our alternative, at least in value, though there may be advantages to the engineering of one method over another. This is now a universal program. We can design it and expect to interchange it with future advances as we need. Let's see this in a demonstration in the Java programming language. At the beginning, we use as function to describe the alternative functions. Notice that the apply on line 3 takes as input something of type C and something of type A, and it returns something of type B. This makes it a function from C paired with A into B. These are the alternatives that we will want to plan ahead for. Our formation rule took a pair AB and made this exponential B to the A. In the Java syntax, we can't use B to the A, but we replace it with the expression EXP for exponential. Next, we look at the introduction rule. The introduction rule challenges us to use whatever alternative method might be available in the future. So we have an alternative function f, and we have a particular chart c. We convert it to c to the f of type b to the a, our exponential. In this demonstration, we're taking the easy way out. We're simply storing the values little f and little c, and we'll come to using them in our elimination rule. In reality, this would be a place where you could begin conversion. For example, suppose we were given a function that was represented as a spreadsheet or a comma-separated value, but we'd prefer to store them as a JSON or some database format. This would be the place where we would convert the given input c and convert it into a new format that could be read in our future apply according to the tools of our engineering. When we look at the elimination rule, at this point we assume that capital F is the representation of our function in whatever format we are engineering ourselves. For example, this may be a data type in a database, or it may be a JSON file or some appropriate technology that we are interested in using. Little a is now a specific application of our data. For example, this might be a recipe which we'll combine with our current nutrition chart to create a nutrition label. Notice that this apply does not depend on a little c of type big C, and that is because we already have data in the format we want. That's the capital F. This is where you have the right to engineer your program however you like. In this example, capital F is my little f. That's the way we are going to apply it in our situation. We combine it with my c and the given value a to produce the right output b. The computation rule guarantees that any alternative result will give the same value as our internal result. In this example, it's not surprising because we've engineered them to be exactly the same thing. But if you were to actually convert something like a comma-separated value to a JSON file or something like it, then you would be responsible for confirming that these are in fact equivalent expressions. If we apply this in a demonstration, we would take a new function from some alternative and some data such as a string, and we would create a new function from our factory in the format we want. In this case, I've called it f as new func. When we apply that to some input, it'll create the data that we are expecting as an output. Notice that you can detect introduction and elimination rules in this syntax by looking for the uses of new. New precedes introduction rules in the Java and C++ and similar types of languages. Likewise, elimination rules are preceded by the name of the data and then followed with a dot. And here we have the same program, but done in two different alternative syntaxes. In the above one, we still see the keyword class. It's producing a formation rule. And again, we use exp. We take the terms b and a, but now our introduction rule is part of that first line. And we're allowed in this syntax to just include the alternative as a function from the pairs CA into B, and any choice chart C to get us started. Our elimination rule, in this case, is allowed to be used the symbol @ similar to what we used in our mathematical formula. Once more, we're not showing off any new engineering, just simply showing that this is possible. This would be the place for you to implement some alternatives, such as conversion of a file format from JPEG to PNG, from CSV files to JSON, or whatever format is appropriate. To apply this function, we would be able to take any alternative, such as the very first place we found the data, surfing the web, or any future advances, such as a new format. Convert it into our exponential, and we'll have taken on those new lessons. In the second code snippet, the keywords have changed, but we allow ourselves similar flexibility, including the ability to write our notation much more mathematically. By whatever notation, this exponential is a key step in building up complicated data types because it allows us to store intermediate representations of functions and thereby add to what we might naturally do in the programming language itself. This data type, the exponential, is an enormously useful way to compress information when we know that we want the behavior of functions, but we don't necessarily want to pay the cost of rewriting new programs between any two function applications. Use this whenever you expect that there will be a reason to encode your data in different ways to produce new functions from the data you have. And be on the lookout for the swapping between pairs and functions of functions. This is an important relationship known as the fundamental theorem of lambda-calculus, which we'll do in another video. Taken together, we have a powerful new tool, a new type of universal construction. It's neither a cone nor a cocone. It's a brand new, independent type of universality. And it might strike you that you could start inventing even other ones by mixing and matching multiple types of constructors. Until next time. That's how you take care of your chalkboard.